In this video, we are going to talk about bond line structures and Lewis structures. So let's begin by talking about the elements that are commonly used in organic chemistry. So there's carbon, there is obviously nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and there's also hydrogen. Some extra ones that you might see sometimes is like silicon, phosphorus, sulfur, selenium. For the most part, you'll see the ones that I drew first. So we need to know how many bonds each are going to make. So hydrogen likes to form one. It already has one valence electron and it wants to get to two, so it's going to form one bond to get there. Elements to the right here, they all want 8 valence electrons. Now in blue, I'm going to write how many they already have. So the ones in this group have 4. These ones have 5. These ones have 6. The halogens here have 7. So the amount of bonds they would form corresponds to how many more electrons they need to get to 8 in their valence shells. So carbon and silicon form 4. Nitrogen forms 3. Oxygen forms 2. Halogens form 1. And the way it looks like, hydrogen looks like this, and this is the bond. The bond is made of 2 electrons. Carbon and silicon, they would look like this. They make 4 bonds. It can also look like that or like that. So it just depends on the situation. You can have double bonds or triple bonds like that. For nitrogen, so nitrogen is going to be forming 3 bonds. And nitrogen usually has a lone pair. Because if you count the total number of electrons here, you have 2 here, 2 here, 2 here, so that's 6. It needs a lone pair to get to 8. So oxygen likes to form 2 bonds, and it has 2 lone pairs. The 2 bonds can also be a double bond, so it can look like this. The halogens, I'm just going to put X. X can be any of these. So keep that in mind. A halogen is going to form 1 bond, and it's going to have 3 lone pairs. So each 2 is a lone pair, and each dot is an electron. So keep that in mind as we begin to look at some examples. So our first example is going to be CH3. CH3. How do we draw the Lewis structure for this condensed structure? So we know that we have a CH3, so that's carbon with 3 hydrogens attached. And we have another CH3, so that's another carbon with 3 hydrogens attached. And all the hydrogens have 1 bond, right? So they're good, but hydrogen here, carbon here has only 3 bonds, each one of them. So if you connect them to each other with a single bond, they're both going to have 4. So this one's going to have 4, and that one's going to have 4. So that's how you know that this structure looks like this. Now let's change this to CH2, CH2. We would have the carbons, right, and we have the hydrogens. So if each hydrogen, or each carbon has 2 hydrogens, so distribute the hydrogens evenly among the carbons. And then you can see here that each carbon has 2 bonds. So this carbon has 2 bonds, and this carbon has 2 bonds. What kind of bond would the carbons need in the middle, right here, in order to get to 4? Because they usually have 4. So if you form a single bond, each carbon would have 3 bonds. But if you form a double bond, each carbon would have 4. So when you have double bonds between carbons, this is called an alkene functional group. So this is just a type of organic compound called an alkene. Now what if we have, let me just redraw this, HCCH. How would we draw the Lewis structure for this? So we know we have a carbon with a hydrogen each, what kind of bond do we need in the middle to make it so that both carbons have 4 bonds, which they need? So we're going to form a triple bond. So now each carbon has 4 bonds. And when you have triple bonds between carbons, this is called an alkyne. Let's look at a few more examples. Let's go over CH3, CH2, CH3. So this is called propane, and the way you draw it is you have 3 carbons, and the carbon on the left has 3 hydrogens, so draw 3 hydrogens for it. And the carbon in the middle has 2 hydrogens, so you draw the 4 hydrogens. And the carbon on the right has 3 hydrogens. And these carbons need one more bond. Well, they need single bonds between one another so that each one of them can get to 4 bonds. So this is how you draw a Lewis structure. Now let's get into a longer chain. Let's say CH3, CH2, CH, actually I drew it wrong, CH, 2CH2, CH3. How many carbons do we have in this? We have 1, 2, 3, 4, 5. So, and then we have 3 hydrogens on the carbon on the left. We have for the next 3 carbons we have 2 hydrogens each. So I'm going to draw those. And the last carbon on the right, we have 3 hydrogens. And then you really only need single bonds between these carbons to make them 4 bonded each. So you can see the problem here is that we have spent so much time drawing all the hydrogens. It's just going to take too long. It's too cumbersome. So the solution to this is going to be bond line structures. So bond line structures look like this. First thing you have to try and figure out is how many carbons do you have in your main chain. So we have here, we have 5. Right, we have 1, 2, 3, 4, 5. So then you start out by, you can do this at first just for practice. You can draw a dot which represents 1 carbon, and then you can draw a line. The line represents the bond to another carbon, and then you just do this zigzag motion until you get to 5. So now we have 1, 2, 3, 4, 5 carbons. Now, if you were to do this quickly, you put your pen on the paper and you count 1, 2, 3, 4, 5. And each intersection is assumed to be a carbon. Like each one of these blue dots is a carbon. And it is also assumed that if an intersection doesn't already connect to 4 things, that the remaining bonds are going to be hydrogens. So for example, on this left side we have, this carbon has only 1 bond, but carbon usually has 4, so it's missing 3 bonds in a sense. However, it's already assumed that this has 3 hydrogens on it, like it does on our structure here. In the middle, for example, let's say, look at this carbon. It has 2 bonds already, and we assume that it has 2 hydrogens. So it just makes drawing long structures a lot easier in organic chemistry. Next example, let's look at CH3, CH, CH3, CH2, CH3. So let's expand this out first. So we have a CH3 on the left, and then we have that connected to a CH. Whenever you see CH3 in the middle, so we see CH3s on the ends. When you see it on the middle, it's going to be called a substituent. So now, what exactly is a substituent? When you want to draw a substituent, you don't go like this. You don't go like that. That would be wrong. What you do is you put it off to the side. And I will show you what that looks like on a Lewis structure in a minute. Then you have a CH2, and then you have a CH3. So these CH3s are always going to be at the end, or to the side. So to draw the Lewis structure fully, CH3 on the left, and then you have a C. So this carbon right here is attached to one hydrogen, and then it's attached to a CH3. A CH3 is called a methyl. So keep that name in mind, methyl. Then we have CH2, which is carbon with two hydrogens, and then we have a CH3 at the end. So you can see here that in our previous examples, we always had hydrogen attached to each carbon, but now we have a methyl attached to one of the carbons. So that's called a substituent right there. Now I'm going to draw the bond line structure of this as well. So in our main chain is every the chain of carbons that doesn't include the substituents. So the main chain, we have 4 carbons, so 1, 2, 3, 4. And then on the second carbon from the left, so this carbon, we have a methyl group. A methyl in bond line is just going to be just draw a line, because it's assumed that at the end here you're going to have a carbon, and it's only bonded to one thing, so the other 3 are assumed to be hydrogens, which is the case here, 3 hydrogens. So let's take a look at CH3, CH2, 4, CH3, 3. How would you draw the structure, the bond line for this one? So first, let's expand this out and understand what the right end means. So we have a CH3 attached to 4 CH2s. So you have a CH2, and then you repeat it 4 times. So that's twice, 3 times, and 4 times. Now on the right end, you have a carbon, a single carbon, and it has 3 methyl groups attached to it. So those methyls are going to be CH3s. Now in order to expand this out, we would think of the main chain. The main chain is, again, the longest chain of carbons. Now the main chain can be this, it can be this, or it can be this. Either way, it's not really going to make a difference. So just count the number of carbons in the longest chain. Let's just go with this one because it looks straight. 1, 2, 3, 4, 5, 6, 7. So we have 7 carbons in the main chain. So I would draw a bond line structure with 7 carbons. So 1, 2, 3, 4, 5, 6, 7. And then in terms of substituents, we can see that at the end we have one substituent. I erased one more thing here. We have a methyl on the second to last carbon, and then we have another methyl on the second to last carbon. So we have 2 methyls on this carbon right here. So we would just draw them like this. Now theoretically, you could also draw those methyls on the carbon on the left, because those 2 structures, that was wrong, sorry. These 2 structures would be symmetrical to one another, so it really doesn't matter whether you go left or right, but it's just easier so that you don't make mistakes that you go on the same side. Next example, let's look at Ch3 Och3. So whenever you see an oxygen in the middle, just in between a hydrocarbon chain, this is called an ether. And there will be other examples where we use oxygen, but in this case it's an ether. So an R can be just any hydrocarbon chain. So the way we draw this is we have the oxygen. We know oxygen usually has 2 lone pairs, as we said, and it makes 2 bonds. It makes 1 bond with the CH3 here, and then it makes another bond with the CH3 here. You can write the CH3 either as this or this. It's just quicker to write CH3 than expand it out. So that's called an ether functional group. Then we have CH3 CO CH3. Whenever you have a COC, this is called a ketone. So a ketone is where an oxygen attaches to a carbon, and then that carbon is attached to 2 other carbons. That's called a ketone. And more specifically, this region of the ketone, where the oxygen double bonds to the carbon, this is called a carbonyl group. And we're going to see a lot more examples with carbonyl groups, but the way you differentiate the functional groups that all have carbonyls is what's attached to the carbon, right? What are these 2 things? So in the case of a ketone, it's always going to be 2 other carbons. The way we draw the structure, we have a CH3 on the left. It's going to be attached to a carbon, and that carbon is going to be attached to an oxygen. And then you continue on with a CH3 on the carbon. So that's the simplest ketone that you can have. CH3 CH2 OH. So how do we draw this one? We have a CH3 on the left, so that's carbon with 3 hydrogens. We have a CH2, which is a carbon with 2 hydrogens. And then we have an OH. Now whenever you see OH, it's going to mean that this is an alcohol. Alcohols have an OH group, which is also known as a hydroxyl group, attached to R, which is just any hydrocarbon chain. So the way you draw in a Lewis structure would be you draw the carbon, the lone pairs, and the hydrogen. More casually or just commonly, the hydroxyl group, or the OH, is going to be drawn as just an OH like that. So you may see it that way, and it's just easier to draw it this way than do all of this. Alright. So now let's look at CH3 CHO. So instead of COH, we have CHO, or not really. Instead of OH, we have HO. So what does this mean? This is an aldehyde. So when we looked at a ketone looked like this. It was an oxygen double bonded to a carbon, and the carbon was bonded to 2 other carbons. In this case, it's in the case of an aldehyde, it's going to be bonded to, the carbon is going to be bonded to another carbon, but then the other carbon is going to be a hydrogen instead. So that's an aldehyde, and a ketone look like this. So the difference is here. So to draw this, we have a CH3, more specifically there. We have a carbon, and then we have a hydrogen, and then the double bonded oxygen. So that's an aldehyde. What if we have CH3 COOH? What do we do in this case? So this is called a carboxylic acid. And the way you tell you have a carboxylic acid is by this pattern of letters in your condensed structure. So a carboxylic acid looks like an oxygen double bonded to a carbon. Then the carbon is bonded to another carbon. And then this end is going to be an OH, just like we saw before with an alcohol. So that's a carboxylic acid. And the way we're going to draw that, we have a CH3. We have a carbon. We have the oxygen. And then we have the hydroxyl, or the OH. You can also do the bond between oxygen and hydrogen, but more commonly it's just drawn as OH. What if we have CH3, COO, CH3? The functional group here, what's specifically important is COOC. This is an ester. Let me draw it in red. An ester, similar to the other ones, has a carbonyl group. The carbon is attached to an oxygen, which is then attached to more carbons, and then the other bond on the carbon is going to be a carbon. So that's an ester. Now to draw this, we have a CH3 on the left, as we usually do. Then we have a carbon. And then we have an oxygen double bonded to it. Then we have the oxygen, which is single bonded to the carbon. And then we have the continuation of the carbon chain. And it doesn't have to be CH3, it can continue going with carbons. But that's the simplest example of an ester. So let's look at the next example. We're going to go with CH3, CH2, and then NH2. Whenever you see NH2, that means that you have an amine. So an amine is any hydrocarbon chain, which is this R thing, that's bonded to NH2. So in this case, we have a CH3, a CH2, and we have an NH2. So nitrogen is going to be attached to two hydrogens, and nitrogen usually has a lone pair. You don't have to put the lone pair every time, but it's just useful to know. Next example, let's look at CH3, CO, NH2. So whenever you see CONH2, there is an amine inside of it, but when you see the CO before the NH2, that's going to be called an amide. An amide is similar to an amine, but there is an important difference. So an amide is an oxygen double bonded to a carbon. One end of the carbon is going to be another carbon. The other end is going to be a amine group. It's going to be an NH2. So to draw this, we have CH3 on the left. We have the carbon, which is double bonded to the oxygen. And then attached to that same carbon, we have an NH2. So that's how you draw the Lewis structure for this amide. Now, just to review on the ones that had the, because many times you've noticed that we've done this, right? This is a carbonyl. So let's just go over a quick review of what they all are so you can put them together. If the carbon is attached to two other carbons, this is a ketone, right? And if the carbon is attached to another carbon and then a hydrogen, this is an aldehyde. If the carbon is attached to another carbon and an OH, this is a carboxylic acid. And if the carbon is attached to an oxygen, and that oxygen is attached to like whatever other carbon chain that keeps going, and then you have a carbon at the other end, it's going to be called an ester. And then lastly, if the carbon is attached to an NH2 at one end and carbon at another end, this is going to be called an amide. In terms of how these would show up in the formula, let me go over that real quick. Ketones are going to have a COC. That's how you're going to see a ketone usually. Should probably draw that in blue. An aldehyde is usually going to be a CHO. So it'll show up as CHO. For carboxylic acid, you're likely to see COOH. For an ester, it's usually going to be COOC. And then for an amide, it's going to be a CONH2. So now let's go over some more examples. So let's go over Ch3 Cn. How would you draw the Lewis structure for this? Whenever you see Cn next to one another, this is called a nitrile functional group, and the way it looks like is going to be a carbon, which is triple bonded to the nitrogen, and then the carbon is attached to whatever else. So the way we draw this, we have a CH3 on the left, so that's going to be a CH3, and then we have a Cn, so you have a carbon on it, and then that's triple bonded to a nitrogen. So that's what it would look like. Now what if we have a CH3 CH2F? So this is called an Alkyl halide or Haloalkane. So this happens whenever you have a carbon attached to either a chlorine, a fluorine, an iodine, or a bromine. So these are all the halogens, and whenever a halogen attaches to a carbon, it's going to be a haloalkane. So in this case, we have fluorine as our halogen, and we have a CH3 on the left side. We have a CH2 on the right side, and then that CH2, the carbon, is going to be attached to a fluorine. And as we talked about, halogens usually have one bond, so this is going to form one bond, this fluorine. And if you were to be precise with the lone pairs, it's going to have 3 lone pairs. So now let's start drawing the bond line structure of some molecules that are going to have based on their names, basically. 3,3 diethyl 4-methyl hexane. So you should be familiar with the naming system somewhat. So if you have a carbon with one carbon, if you have a hydrocarbon chain with one carbon, it's going to be methane, and then 2 carbons, it's going to be ethane, and then I'm going to continue on. We have propane, butane, pentane, hexane, heptane, and octane, nonane, and decane. So hexane would be 6 carbons, sorry. An ethyl is 2 carbons and a methyl is 1. However, the YL suffix means that it's missing a hydrogen. So if we have hexane, that means we have 6 carbons. So if you remember the way we drew the bond line structures, it would be count 1 when you put your pen on the paper. So 1, 2, 3, 4, 5, 6. And then we can actually number the carbons. So carbon number 1, we could say 2, 3, 4, 5, 6. Then based on the numbers here given and this name of the substituent, we could actually draw the substituent. So it says 3, 3. That means we have 2 things on carbon 3, and it's going to be an diethyl. Diethyl means 2 ethyls. An ethyl is a CH2, CH3. In bond line structures, an ethyl is going to look like this. And then we have on carbon number 4, which is here, we have a methyl. A methyl is just a straight line. That means we have a CH3 at the end. On the ethyl, it means we have a CH2 here and CH3 at this end. Next example, we have a 2,2,3,3 Tetra methyl pentane. This is a little bit crazy because we have 4 methyls. 2 of them are on carbon 2. The other 2 are on carbon 3. So we have a pentane, which means we have 5 carbons. So if we count 1, 2, 3, 4, 5, carbon number 2 has 2 methyls. So there's 2 methyls. Carbon number 3 has 2 more methyls, and that's our structure. Now we've looked at alkanes so far, where the carbons only have single bonds between them, but in this case we're going to have at least 1 double bond between the carbons. So we have 2 pentene. How do we draw this? Now pentene is basically pentane, but an alkene version. So it's associated with having, once again, 5 carbons. So if I draw 1, 2, 3, 4, 5. When you see number 2 before an alkene like this, it means that the double bond is on carbon 2 and 3. So if I count the carbons, number them, if the double bond is between 2 and 3, you pick the lowest number. So that's why this is 2. If the double bond was here, you pick 1, so this would be 1. So, but in this case, it's between 2 and 3. So that's the structure for this alkene. Let's draw 2-chloro 3-fluoropentane. So once again, pentane is 5 carbons. And if we want to, I'm not going to number them this time, it's just 1, 2, 3, 4, 5. You already know that. On carbon number 2, we have a chlorine because it's chloro. On carbon number 3, we have a fluorine. So that's F. And that's the structure. Next, we're going to have a 3-chloro, 2-ethyl, 1-hexene. So whenever you see hex, that's associated with 6 carbons. So we're going to draw a 6-carbon chain, 1, 2, 3, 4. And so it would look like this, but the general guideline I use is that the M, or the McDonald's sign, is going to be pentane, or 5. So if it's 6, you just add one more line. Now in this case, carbon number 3 has a chloro, so this would be carbon number 3. So we'd put a chlorine on it. Carbon number 2 has an ethyl, so this is carbon 2. We put an ethyl on it. And then carbon number 1 has a double bond because the 1 comes before the word hexene, and hexene has the suffix ene. So let's put the double bond right here. And that's our structure. Now when it comes to these alkenes, or these hydrocarbons with a double bond between the carbons, you need to understand the difference between trans and cis. So let's draw a trans 2-hexene and cis 2-hexene and understand the difference between a cis isomer and a trans isomer. So let's forget about these with the hexene for a moment. Let me draw a butene. Drawing 2-butene right now. And I'm going to draw Cis2 Butane as well. So the difference between these two structures is that on the left, the trans side, you can see that the CH3s are on different sides and that the hydrogens are also on different sides. But on the right side, the methyls are on the same side and the hydrogens are also on the same side. So with cis, it's going to be on the same side. With trans, it's going to be on different sides. So knowing that principle, let's now start to draw trans 2-hexene. So hexene has 6, so we're going to go 1, 2, 3, 4, 5, 6, and it's going to be on carbon number 2. So if you imagine carbon 1, 2, 3, it's going to be between 2 and 3. So 2 is the lowest number. So it's going to be right there. And this is already a trans structure because if you imagine these being the 2 carbons, the double bond is in between. One methyl goes this way, the other methyl goes this way down. And then the hydrogens are so if methyl goes up, hydrogen goes down. And then on the other side of the bond, you have hydrogen going up. So you don't have to draw your hydrogens, but that's just for showing you the difference between the cis and the trans. Now for the other one, I would draw it like this. So I would start, so with the cis, I would just start and then do a straight line and then follow the same direction down. And then, so far you have 1, 2, 3, 4. So you need 2 more carbons to get to 6 because this is a hexene. So that's what the structure looks like. So the double bond is going to be right here. And as you can see, the hydrogens are going to be on top. Methyls are going to be on the bottom. These are the methyls. At least as far as, if you don't count this, then it's a methyl. So that's the difference between cis and trans and how you draw it in bond line structures. Now let's go over how we can draw cis and trans isomers within a cyclic molecule or a ring. So we have cis 1,2-dimethyl cyclohexane. So cyclohexane is going to be, it's going to look like a hexagon. So each end is a carbon, and we have two methyls, so one on carbon 1 and another one on carbon 2. It doesn't matter which one of these carbons you pick as number 1, you can pick any of them. But then 2 has got to be next to it. So in order to make them so that they're cis, there's two ways we can do it. We can either go with a dash on both, or we can go with a wedge on both. So we could either do that, or we could either go like this. The dash is coming out of the page, and the wedge is going into the page. And the reason there's no thing on the end of these, we could put a CH3 if you want, but it's assumed at the end you have a carbon, and then you have the 3 hydrogens attached to it to make it so that the carbon is bounded to 4 things. Now, what if we were to draw this as trans? The trans version would look like this. The trans isomer would have one dash and then one wedge. So now let's look at our last example. It looks a little bit crazy. So we got 2 amino 3 ethoxy 4 hydroxy, and then we have 5 methoxy 6 oxoheptane. Heptanoic acid, I should put. Okay, so this looks crazy, but I'm going to tell you what these mean. So first of all, we have heptanoic acid. This is how you name a carboxylic acid, and because we have the suffix hept, we're going to go with 7 carbons. So 1, 2, 3, 4, 5, 6, 7 carbons. And then I'm going to decide that we're going to start counting the carbons from left to right. When you have a carboxylic acid, the carboxylic acid group is always going to be at one end of the molecule. It can never be in the middle. So because it has a hydroxyl like that, or really a carbonyl like that, and then you have the hydroxyl right here. Then I should really draw this better because it should more like that. So that's carbon number 1. The carboxylic acid is always going to be on number 1. On number 2, we have an amino. What does an amino mean? That just means NH3. So, or NH2 really. So whenever you see an amino, it means NH2. Now, what exactly is ethoxy? Ethoxy is going to be O, CH2, CH3. You could also write it like this, but usually you'll see it as OCH2, CH3. Then number 4, we have hydroxy. Hydroxy is going to be the same thing as hydroxyl. So it's going to be an OH. Now we have 5 methoxy. Methoxy is similar to ethoxy, except that you have OCH3. And then for 6, you have oxo right there. Oxo means that you have an oxygen double bonded to the carbon. So to review, we have an amino group, we have an ethoxy substituent, we have methoxy, we also have hydroxy, and then we have oxo. So just memorize those names for these functional groups. So that's it for this video. I hope it was helpful. Thank you for watching.